Alright, this unit is on momentum. So momentum is a vector quantity that we use that helps us find a lot of things, but if we want to look at it basically, you can think of it as how hard it is to stop something. So we can say that a bee moving at 10 meters per second has momentum, but a baseball moving at 10 meters per second has a lot more momentum because it has much more weight and more mass to it. We can compare someone riding on a bicycle really quickly. They have momentum. A train moving slowly has much less speed, but because its mass is so big, it has more momentum. Now the symbol for momentum is P, and is a vector, and the formula is mass times velocity. And that is how you find the momentum of something. So if we take a look at a simple example like this one, where you have a ball moving at 40 meters per second, you always start with the formula, of course. And remember, those little arrows on top are the half arrows and the vectors. And that is the momentum of the ball, 12 kilogram meters per second. Now if we look at an example a little bit harder, last year when we did momentum, it was always conservation of momentum. And so it was always the momentum before equals momentum after. And this is true. And this is why momentum is such a great thing to use. It's because momentum is never lost, it's always conserved. We say the same thing with energy. Energy is never lost, it's always conserved. But energy is difficult to keep track of. When you have a car collision and one car collides against another, we have the mashing of metal and we have heat given off and there's friction and all sorts of things. It's really difficult to keep track of. Only if we had this closed system where we could measure all the changes in temperature could we really keep track of conservation of energy. Momentum is not like that. Momentum is much more simple, or I guess it's simpler to keep track of. It's just m1 v1 before equals m1 v1 after. Or if you have more than one mass, you have m1 v1 before plus m2 v2 before equals m1 v1 after plus m2 v2 after. And if you have a completely inelastic collision, that's a collision where they're stuck together, then it might actually be m1 plus m2 times your speed after, because they're stuck together. But this way of approaching it, it's true that momentum before equals momentum after, but as far as just writing out numbers like you did in grade 11, this doesn't work often in grade 12 because we're dealing with angles in different directions, and because momentum is a direction, we can't just add the numbers on both sides. We do have to watch out for the directions and the angles and add vectors in the way that we know how to add vectors. So if we take a look at this next example, it's a little bit more difficult. We have a pigeon flying south, like so, and it collides with a crow flying west, like so. Now what we're looking for is the final velocity, because they're in a completely inelastic collision. You can't add the velocities because we have objects of different mass, and we don't know what else is happening, so what we can do is we add the momentums, and once we have the final momentum, we can solve for the velocity. So the first thing is, if I take a look at that, say this is bird 1 or pigeon 1, momentum 1 and 2, and so the result is going to be something like that. So first find the individual momentums for each one. So there's m1v1, or in this case your pigeon is 0.5 kilograms times 30 meters per second, and that works out to 15 kilogram meters per second. Our second momentum, the one of the crow, is 1.2 kilograms times 22 meters per second equals 26.4 kilogram meters per second. So to find our resultant momentum, or momentum after, then what I'm going to use, since this will be a right triangle, I'm going to use Pythagorean theorem and say the momentum after squared is equal to momentum 1 squared plus momentum 2 squared. So momentum after squared is equal to 15 squared plus 26.4 squared So if we work this out, it becomes 30.3638 kilogram meters per second. And since they are stuck together, then if we want to solve for our velocity, we know our momentum, it's going to be our total mass times our velocity after, or our velocity after is going to be this new momentum divided by total mass, which is 30.3638 divided by 1.2 plus 0.5 kilograms, which works out to 17.861 meters per second. Now this is a vector, so we are going to need an angle. So we have one momentum, which was 15. We had the second momentum, which was 26.4. And so to find our angle here, I'll say that this is my adjacent side, and this is my opposite side. So tan theta will be opposite over adjacent. Angle will be inverse tangent of 26.4 divided by 15, which is 60.4 degrees. So if I write out then my final answer, the resultant velocity will be 17.9 meters per second and 60.4 degrees west of south. Now the last thing I want to talk about regarding momentum is impulse. And impulse can be a tricky idea because it's set up a little bit different. We refer to impulse as a change in momentum. And so change in momentum can be P final minus P initial. So if I'm driving along at 50 kilometers an hour and my car gets bumped from behind and it moves a little faster forward, it received an impulse. Impulse can also be described a different way. Impulse can also be a force times change in time. So the car from behind exerted a force over a short period of time, then it passed an impulse into my car. So there's two ways to approach it. Impulse could either be defined as change in momentum or force times change in time. Now because impulse actually has two formulas, we can make these formulas equal to each other in order to find sometimes things that we are looking for. We can use force times change in time is equal to change in momentum. Now the example I want to go over doesn't involve force times change in time. It's just a change in momentum question, but it is one involving vectors and directions and angles, and it can be a bit difficult at first because we've learned that vectors, you can only add vectors. You can never subtract vectors. Well, the problem with that is what happens if you actually need to subtract a vector. So impulse, we know, is going to be P final minus P initial. So we take a look at this example. We have a soccer ball moving south at 26 meters per second. It collides with the defender's head. So let's just say we have a soccer ball. It's moving south this way. It collides with a defender's head and then travels east. So what we need here is an impulse going sort of this direction to stop the ball from continue moving south, and to force the ball to go east. So, as I said, to find change in momentum, what it is P final minus P initial, and P final is going this, and P initial is going this way. But since we can't subtract vectors, what we can do is we'll say change in momentum will be P final plus the negative of P initial. And so P final plus P initial going north instead of south. And so first thing we want to do is calculate P final, P initial. P initial is going to be 0.45 kilograms, 26 meters per second, and that works out to 11.7. And P final is 0.45 kilograms times 31 meters per second, and that works out to 13.95 kilograms times meters per second, kilograms times meters per second. So I will use Pythagorean theorem here, and we'll say that if we add head to tail, this is P final, this is P initial, will give us the change in P, or the impulse. P initial is 11.7, P final is 13.95, and so using Pythagorean theorem, then our change of momentum is going to be P initial squared plus P final squared. So our change of momentum squared is going to be 11.7 squared plus 13.95 squared. And if we work it out, then our change of momentum is 18.20694, and I'm trying to keep as many numbers as I can to keep things accurate. So we also need an angle because this is a right triangle. So if we come back to here, and if I draw this out, if I have 11.7 plus 13.95, and if I want an angle theta, then I'm going to call this my opposite side, this is my adjacent side, so I'll just use tangent again. So my angle will be inverse tangent of 13.95 over 11.7. So the angle works out to 50.0 degrees. So if I write out my answer, the impulse is 18.2 kilogram meters per second, 50 degrees east of north. Okay, so then once again, we have a soccer ball coming down this way, hits the head, ends up going that way, so we need an impulse, this one here, 15 degrees east of north, stopping it from going south and forcing it to go east.